Thanks to all for coming to hear about my research work. So, this talk is about efficient algorithms for geometric problems. And in this talk, I will start by motivating the area of computational geometry a bit. And so my work is about designing algorithms for problems with a geometric flavor. So one of the subfields of algorithms that I work quite a lot is parameterized algorithms. So I'll introduce parameterized complexity, tell you what it is and how it is involved with my work. And after that, we'll hopefully see some areas of geometry, some areas in geometry where I work in. It's a geometric set cover and heating set, and art gallery problems, and bichromatic problems on bichromatic point sets. And we conclude with the future direction that my research will take. Okay, so I'll start with this question. As I mentioned, I worked in algorithms with a geometric flavor. So, given a problem which is stated in terms of geometric entities like points or polygons or half planes, I would try to solve these problems efficiently. When I say efficiently, I'll try to design provably efficient algorithms. So my work is more or less very theoretical. So we try to design provably efficient algorithms for geometric problems. So first question is why geometry? Like why do you want to study problems in geometry? And simple and very intuitive answer is, see, geometry is everywhere. Geometry is all around you, right? So, like for example, if you are considering building a home or building a house or building an apartment complex or building an institute like this or building for an institute like this, it all starts with a geometric figure like this, the floor plan of it, right? So this is a polygon. In fact, like you can think of it as a polygon in 2 dimensions. Right? Or if you so this is a representation of an IC chip. So you are in VLSI design or okay. So these entities can be represented as an arrangement of a number of geometric figures. Like in this case, it's more or less axis parallel rectangles which are connected by rectangular regions. Or if you are working in molecular structure, again it's representing some geometric representations that comes into play. These examples were more or less very intuitive to see how geometry plays a role. There are like more non-intuitive, okay, maybe it is intuitive to all of you. There are other areas, like for example, representing data. It's quite popular nowadays, I think. So you want to store information about, for example, you want to store information of all students at IIIT-B. So this information can be stored as points, as a point set in a geometric plane, probably a high dimensional geometric plane. Now this problems involving this data, like you want to search in the database, you want to search in a table, it is equivalent to a geometric searching problem. Okay. So here there's a figure. So we look at problems which take as input a large number of geometric entities like lines, polygons, etc., and try to give a solution. So this is broadly what computational geometry is about. Again, it's a very rough definition. And the area of computational geometry came in around 60s, I think around in 1964 people started studying officially the geometric problems, and it picked up interest mostly because of 2 reasons, I'll say. One is large number of applications where these algorithms can be used in, like it's a wide range starting from geometric information systems, robotics, medical imaging, VLSI design, data mining, and so on. And second is because of the beauty of the problem and beauty of the techniques that's used to solve the problems. So in my personal opinion, these two are like equally important for studying any problem, whether you can use it in any or whether you can apply it anywhere, or second is like this a problem has enough beauty in it, or this problem excites you theoretically also. And so although there are many applications, most of my work is not it's not based on a particular application. So I'm not trying to solve any particular applications. I work on more abstract models, like so many of these application related details are abstracted out, and we work in a more abstract setting. And try to, as I said, I try to design probably efficient algorithms, theoretically efficient algorithms. Okay, and in this algorithm design, one particular area of algorithm design I work more quite a lot is parameterized complexity. So for some time I will explain what parameterized complexity is. So the motivation for field parameterized complexity is NP hardness. So we know that many of the problems that we encounter are known to be NP hard. Even many of the geometric problems are NP hard. Now what do you mean by saying, what are the implications of saying that a problem is NP hard? Right? So you can say it like, so if let's say pi is NP hard, the problem is NP hard, what are the implications of that? It says that unless P equal to NP, of course. So we work on this conjecture, P not equal to NP. So unless P equal to NP is true, pi cannot have an algorithm that solves pi optimally. Okay, what do I mean by an optimal solution is the exact value of a solution. For example, if you are trying to find the minimum cost of a spanning tree in a graph. So there is like one particular value which gives you the minimum. So that is the exact solution for that. Makes more sense in optimization problems. So you cannot find an algorithm that solves pi optimally, and also that solves all instances of pi. Okay, you take any permissible instance of pi, you cannot solve it optimally in polynomial time. Okay, so these three things together is not possible, of course, unless P equal to NP. So you cannot solve all instances of pi optimally in polynomial time. But it can be seen that in many cases, if you take only a subset of these three conditions, we get efficient algorithms. For example, if you ignore optimally, see, I'm not looking for an optimal solution. I'm looking for a solution which will solve all instances in polynomial time. So this may be possible for many problems. This is what we call as approximation algorithms. So yeah, approximation algorithms in polynomial time. Yes. The exact value of the solution. Okay. So for approximation algorithms or polynomial time approximation algorithms solves all instances, gives a solution that might not be optimal, but it is not very far from optimal. Right? And similarly, if I say that, okay, I don't want to solve all instances, can I solve some instances? For example, this we call EC instances of the problem. This is also possible because, like, for example, some problems, take for example some graph problems, they may be NP hard on general graphs, but they may be polynomial time solvable on some special classes of graphs, like bipartite graph or planar graph, for example. So again, with the EC instances, there is it's natural to ask this question: how do you find the EC instances? Which are the EC instances? I'll come to that shortly. And next is, okay, I don't care about polynomial time. I just want an exact solution, and I want to solve all possible instances. So these are exact exponential algorithms. Okay, So the running time will be exponential, but it's solved exactly. Now taking this thought forward, okay, this is true for many NP-hard problems. So many of the NP-hard problems can be solved in exponential time even by brute force. Even like brute force algorithms that run in exponential time. Okay, so this is, yes. Yes, it can be, yes. Right. Yes, exponential, okay. So sometimes brute force can be like really bad. Okay. So NP-hard problems can be solved, many NP-hard problems can be solved in exponential time just by using brute force. Okay. So parameterized complexity, okay. So before, like this is an example. So assume this is a representation of a road network in a city. Okay, so you have, so each, this is a road and roads converge at what we'll call them junctions. Okay, and let's take this. So city authorities want to make the city safe. City wants to make the city road safe, and assume for that they decided to build police stations or police control booths at which is near to each road. Okay, so the question is how many police stations you have to build. Right? So like for every road, I want to build. So if you take this road, okay, so I want to build for every road I need this. So there should be a police station at one endpoint, at least one endpoint of the road. Okay, so for example, like this. See, every road I have a police station near to it, so that people need any help easily available. Okay, this is just another example. Now this can be represented as a graph problem. This is very easily seen as a graph problem called the vertex cover problem. So what I do is, what is my graph? So for every road, I built a graph like this. Every road is an edge in the graph, and the junction is the nodes in the graph, or vertices in the graph. Okay, and what do I need? For every edge, I need at least one of its endpoints to be chosen. This is nothing but the classic vertex cover problem. Okay, so this is the graph theoretic representation. Given a graph with n vertices, find a vertex cover of minimum size. Of course, usually city authorities don't have infinite fund, so they don't want to build many police stations. They want to build as the minimum that will serve the purpose. Okay, so we are looking for a vertex cover of minimum size. Now, how can we solve it? What will be the brute force algorithm to solve it? Right? It's easy to see. So, just you take, you know that a vertex cover is a subset of V with some properties. So, take every subset, check if it is a vertex cover, and of all the subset which is a vertex cover, take the one which the minimum size. Okay. So, it's basically exhaustive search. You take every possible subset and check whether it's a vertex cover and find the one which is of minimum size. How much time will this brute force algorithm take? Okay, so checking whether a subset is a vertex cover can be done in polynomial time, and finding a minimum from a set of subsets, that is also polynomial time. But we are doing this for every subset of the vertex, right? So there can be 2 power n subsets. Therefore, the running time for this brute force algorithm is 2 power n and some polynomial in n. So I'll use this notation to hide the polynomial factors. So let's say that it is 2 power n time and polynomial n. So this is the brute force algorithm, and see, I can also ask the vertex cover problem in a different way. That is, does there exist a vertex cover of size k? Right? So again, going back to a road network and building police stations example. Usually you have a budget for building for any reforms, right? So if you want to build a number of police stations, you have a fixed budget, and you know that, okay, you can build only at most K police stations, you have the budget for it. So you are only interested in answering the question whether you can make the city safe with building K police stations. Okay. So similarly here, does there exist a vertex cover of size K? Again, what will be a brute force? It's a similar algorithm. So you take every subset of size K and check if it is a vertex cover. And what will be the running time for this? Again, checking whether it is a vertex cover, it is polynomial time, and yeah, there are n power k out of n power k subsets of size k. So the running time is n power k. Okay. So now enter parameterized complexity. So we have brute force algorithms which runs in 2 power n or n power k at time. For parameterized complexity, try to solve an NP hard problems more efficiently than brute force. How do I define efficiency here? Right? When I say, like, of course we are not looking for polynomial time algorithms, but you need to be more efficient, comparatively more efficient. How do I define that efficiency here? Is okay. So as I said, you cannot hope for polynomial time running time because that will prove that P equal to NP if it's an NP hard problem. Okay. So there should be some exponential factor in the running time, but I want to make this exponential part of the running time independent of the input size. Okay. So in the previous running times, 2 power n is exponential in n. Even n power k is exponential in n, right? So n appears in the exponential part of the function. But now in parameterized complexity, what we are trying to do is make the running time. Running time will have a function in input size which is purely polynomial. Okay, but there should be some exponential factor in the running time, right? And that I will limit to what is known as a parameter of the problem. Okay. So here we have so we want to design algorithms with running time polynomial in input size and exponential, probably exponential in what is known as a parameter. Okay, and parameter is a value you assume it is much smaller than input size. So intuitively it's okay to be exponential because it is much less than the input size. In our assumption, input size can grow, but parameter I define as something which is small, which is much smaller than the input size. To state it more formally, a parameterized problem, okay, so before I'll come to this example. So coming back to a vertex cover problem. So given again, does there exist a vertex cover of size k? For example, I am taking k as a parameter now. Okay. Yes. It's usually k, but doesn't make. Oh no, not like that. Okay, I'm not assuming k is a constant. K can, what I'm assuming is k is a positive integer which is small. It's not a fixed constant. It's not a fixed constant. Okay, then it becomes more specialized when I say it is k equal to something. Right. So okay, so okay, given a graph, does there exist a vertex curve of size k? And I take k as parameter, which is okay in many applications because usually, like the road network example we saw, a city will have a number of roads but limited budget, right? So most of the applications, the solution size is this in optimization problems, or okay, I won't say optimization. So we can it's okay to assume that we are looking for a solution which is of size very small. Okay, so I'm looking at, so I'm taking k as a parameter now. Okay, now I want a running time which is better than 2 power n or n power k. Okay, so Okay, so this is the brute force algorithm we just saw. Okay. Now, can I do better than n power k? That's my question. So this is an algorithm. So this is the question. Does G have a vertex cover of size k? Now you can say this, right? So take any arbitrary edge in the graph UV with endpoint UV. If G has a vertex cover of size k, then we know that either U or V belongs to the vertex cover, right? By definition of vertex cover, one of them it should be in the vertex cover. Now assume G has a vertex cover of size k, and we know that either U or V is in it. What does it mean? It means that if you take U in it, let's assume that U is in the vertex cover. You add U in the vertex cover, delete all the edges, use part of. The rest of the graph needs to be covered using k minus 1 vertex, right? Because you have already used one vertex. Right? Similarly, if you can take V, you can assume V is in it, and then the rest of the graph has a vertex cover size k minus 1. So this is this is equivalent. That G has a vertex cover of size k is equivalent to saying that either G minus U has a vertex cover of size k minus 1, or G minus V has a vertex cover of size k minus 1. Okay, so it's enough to prove the second part. So you can prove, you want to prove whether G minus U has a vertex cover of k minus 1 or G minus V has. And how can we prove this? Can use recursion here. Okay. So it's easy to say, right? When k equal to 0, to check whether, how will you check whether a graph has a vertex cover of size 0? It is same as checking whether the graph is empty without any edge. Right? That can be done in polynomial time. Okay. So there is a recursive solution for this, which runs in 2 power k algorithm. Okay. And of course there is a polynomial in n with it, which I am hiding in the notation. Okay. So now if you compare 2 power n power k with 2 power k, okay, when k is small, this is more efficient than n power k algorithm, right? Like even when n is growing, in this running time, okay, even when n is growing, it's not an exponential growth, it's only polynomial. And by our assumption k is small, 2 power k is, we are okay to accommodate that in our running. Okay. So this is the idea of parameterized complexity. So in parameterized complexity, we study parameterized problems. So usually in algorithm design, you have problems where you specify its size. So here you have the input and its size, and also a parameter. And parameter is an integer considered to be much smaller than n. That is the assumption. Okay. And under this assumption, a parameterized problem, we say that we are looking for algorithms like this. Okay. So a parameterized problem is said to be FPT, or fixed parameter tractable, if it can be solved by an algorithm which runs in time f of k polynomial in n. So it is on polynomial in n. F of k can be an exponential function, but it is independent of it. So you can say this is efficient when k is small. So this is what we are looking for. So we are looking for a polynomial in n and f of k algorithms when k is the parameter. Okay. And natural question to ask is, see, in every algorithm design technique you have come across some sort of interactability, right? For example, polynomial time, when you study polynomial time algorithms, we say that, okay, there are problems which most likely do not admit polynomial time algorithms unless the standard complexity theoretic assumptions. Similarly, for approximation algorithm, you might have seen there are problems which will not admit good approximation algorithms. So you can ask the same question here. Okay, so we have defined FPT algorithms. Does every parameterized problem admit an FPT algorithm? So answer is most likely no. Okay. And so there are intractable problems also, and okay, so there are problems for which FPT algorithms are not expected to exist, and again this this is based on the assumptions of in complexity theory, things like P equal to NP. Okay, and these problems is SPT intractable problems. We say that they belong to a complexity class, or they belong to a hierarchy of complexity classes. So they are called W hard problems. So this is a W hierarchy, and we have the class called FPT, which is analogous to P in polynomial time. That is, it's a complexity class that contains all FPT problems, all parameterized problems for which FPT algorithms exist, and the problems which are believed to be hard or which is believed to be intractable in FPT, they belong to a class WI. Okay, and this is it. The class FPT is contained in W1. We have, again, as I said, there is a hierarchy of classes, W1, W2, and so on. But okay, so even though they are like different classes, or we believe them to be different classes, but from the perspective of algorithm design, they are all kind of equal. Like none of them have a FPT algorithm, or expected to have an FPT algorithm. Okay, so. Oh, okay. So we have W1, W2, W3 onwards. So this is the assumption that Wi is contained in Wj if I is less than j. If I is less than j, then Wi is contained in Wj. Okay. So there is like when you go to the definition of the class in terms of Turing machines and all, they have some meaning. But for again, from the point of algorithm design, they are all hard problems. Okay, right. And your assumption is this: FPT not equal to W1. That analogous to P not equal to NP. Of course, it's easy to see, right? If P equal to NP, this collapses, right? FPT doesn't have any meaning if P and NP are same. Okay, so okay, and some problems which are shown to be W hard are okay. So all of them are graph problems. K-clique parameterized by the solution size. All of them are parameterized by solution size. So is there an independent set of size K with K as a parameter? It is also W hard. K dominating set. Okay, so parameterization by solution size is very common. It's usually referred to as a standard parameterization. It's very commonly studied for all problems. And in addition to the solution size, the parameter can be a structural parameter also. Like, for example, if you are in a graph problem, some structural for example, the maximum degree of the graph, or the genus of the graph, or yes, some other parameter like that. They are all they can be parameters. Okay, right. Okay. So next, I'll come to the next interesting topic in FPT, known as the kernelization. So. Yeah, it all follows from P not equal to NP. Yes, right. Hierarchy and set, of course, FPT is, yes. Okay. Okay, so kernelization is again an interesting topic in FPT. Why? Because, see, it deals with, okay, you start with a parameterized problem NK, and kernelization deals with some pre-processing of the input. Okay, so so you start with an input of size n and a parameter k, and you pre-process in polynomial time, okay, to get a smaller instance. Now, how do I define small? Is you start with an instance of size n, and after pre-processing you get an instance of size g of k, where g is a function independent of n. Okay, so you start with a input of size n, and after pre-processing in polynomial time, you get a smaller instance which is just a function whose size is just a function of k, the parameter. And of course, it's a parameterized problem. So here you have a new parameter k prime, which is again just a function of k. So you okay. So here the important thing is it is independent of n. After pre-processing, you get a new instance which is independent of n, and this new instance is called the kernel of the problem, and this polynomial time reduction is it's referred to as kernelization. Okay, so yeah, and yes, okay, this is an important thing. So also, when after the reduction we get an equivalent instance. That means this is the starting instance is a yes instance if and only if the kernel is a yes instance. So instead of solving this, you need to solve just the kernel. Okay. So now I think you can see why the importance, right? So if there is a kernel, we can immediately say that it is FPT. Oh, okay. So formal definition. So problem is said to admit a g of k sized kernel if there exists, if in polynomial time you can reduce the problem to reduce the instance to a reduced instance of size g of k while preserving the answer, and also when g is okay, the size of g, the function g is it's what you call as the size of the kernel. For example, if g is a polynomial function, then we say that the problem admits polynomial kernel. And yes. Mm-hmm. No. Okay, so if you can, if you can solve the kernel in polynomial time, it's a polynomial time algorithm, yeah, right? So the entire complete class would reduce. Okay. So kernel doesn't say that. Kernel says that its size is small, but it doesn't mean that. Yeah, it can. G need not be exponential. Even if G is polynomial in K, doesn't imply that there is a polynomial time solution to it, right? Yeah, but if I can decide on that, then it is a polynomial. Yeah. Map to the problem. Then the entire set of yes. So if you can decide the kernel in a polynomial time, of course, the problem you started with can be decided. Okay. Right. And the presence of kernels, if a problem admits a kernel, it implies that the problem is in FPT, right? Can you see how? Because see, here you have this, you say that these are equivalent, and the size of this is independent of n, it's just a function of k. So even if you do brute force on this, it is still FPT time. Even if you run a brute force algorithm on this, it is only exponential in k. And what is the running time in n? It is this polynomial time. So you have a kernel, okay. Presence of kernel imply that the problem is in FPT. Similarly, not similarly, it can be shown that a problem is, if a problem is in FPT, then it admits a kernel. Okay, it is not as straightforward as this, but you can think about it. So this is the result. A kernel, a problem is in FPT if and only if it admits a kernel. Okay, and kernelization is important, and it's usually well studied because of this reason. See our pre-processing is polynomial time, right? And you get a smaller instance. So when you work in a with a yes. No, both. Both are bounded by a function of k. Right. Yes. Okay, and the think you just mentioned why kernels are important, right? So even like theoretically there, like it's okay. Theoretically also the running time will improve when you work on a kernel, and practically also you have like polynomial time pre-processing or reduction, and you're working with smaller instances. Okay, so kernelization usually it's seen that even other techniques, when you combine it with kernelization, it gives theoretically better running times, also practically better running times. So for the practical implementations of this algorithm, they use kernelization quite a lot. So you can yes. For practical algorithms, you usually do some pre-processing, a fine-check kernel, and then use some other technique. Okay, so it gives a better running time. Okay, and that also that's why you try to optimize the size of the kernel also. Like, see, g of k can be an exponential function, but it is particularly interesting if it is a polynomial function. That implies better running time. Okay, so you try to optimize this when you get a kernel. Of course, any FPT algorithm, FPT problem has a kernel, but you'll try to come up with methods to get polynomial kernels, and even further try to optimize it, like from an n-cube kernel, try to optimize to n square and so on. Okay, so then, so when you're in a parameterized complexity field, what are the questions that you usually study for a given problem? So first question is, of course, to identify good parameters. This is similar to identifying EC instances, right? So for when you are investigating a problem, what are the parameters which admit FPT, good FPT algorithms? So this is kind of equivalent to finding EC instances. And next is, okay, once a parameterized problem is defined, of course, you want to know, does there exist an FPT algorithm, and also does there exist a polynomial kernel? And when these questions say yes, again you go back and try to optimize. Like, okay, so you come up with a solution. You say that, okay, there is an FPT algorithm which runs in k power k time. Okay, can you optimize it into, say, c power k time, which is better? You know, this is particularly better because it's all exponential functions, right? So even if an introduction, even a modification or a improvement from 2 power k to some 1.9 power k is very important practically. Okay, so you try to optimize this. Similarly for kernels, as I said, when you are particularly interested to find if there exists polynomial kernels, and further optimizing the size of the kernels. Okay, and again lower bounds. Like, it's referred to as fine-grained complexity analysis. So once you have an algorithm similar to what you do in polynomial time or approximation algorithms field. So when you have a FPT running time, you have a matching lower bound. Proving lower bound, saying that, okay, we cannot do better than this. Similarly for kernels, you can like proving results something like, okay, you cannot get a kernel better than some particular G of k. Okay, so proving these kind of results are also interesting. Okay, so these are this is a brief introduction to parameterized complexity, and now I move to some of the geometric problems I work in. First is, okay, very general problem. I'm sure many of you have already know about it. A geometric set cover or heating set problem. So maybe I'll just go a little fast here. So range space, it's defined. It's a pair which consists of a universe of n elements and a family of subsets of elements in the universe. For example, if you take all the students in IIIT as a universe and take each subset as students in a particular course, it's a range. So the subsets are sometimes referred to as ranges. So range space, it contains universe and a family of ranges. And geometric range space, it's more general than what I have written there. So in geometric range space, the universe is a set of geometric entities, and subsets or ranges are defined by a geometric property. So, for example, P is a set of n points in R square or 2-dimension, or you can think of any dimension, and the subsets are defined by intersection of the point set with geometric objects. Okay. For example, yes, you have points. You have, let's say this is your universe, and you have a family of disks. The ranges are defined by those disks. What do I mean by that? Is you take an object in the family, let's say this disk, and all the points inside the disk form a range. So these 3 points form a range. Okay, and similarly, like all these points form a range. So can be seen immediately that geometric range space has more structure than an abstract range space, right? So in an abstract range space, number of ranges can be as large as 2 power n, where n is the universe size, whereas geometric range spaces may not be possible. For example, in this case, you can see that, you take this point and this point. You cannot have a range containing only those points. Why? You cannot have a disk containing only these 2 points and no other points. It is not possible. So, because of the structure of geometric objects, or the structure of geometric property that is defining the range space, geometric range space also has more structure, and therefore many problems give better results than abstract range spaces in geometric range spaces. Okay, so one such problem is heating set problem. So heating set is this. So if you take right, so it's a subset of the universe such that every range contains at least 1 point from the subset. Okay, it's a subset of the universe, and in every range there is a representative from it. So it's called a heating set. Okay, so you can see that it is vertex cover problem is special case of heating set problem. Right. So okay. So heating set is a subset of the universe such that every range contains at least 1 element in it. So just to show an example, take this range space. So these points inside each disk is a range, and see these 2 points, these 2 red points is a heating set. You take any disk, it contains at least one of these 2. So it forms a heating set. And an interesting algorithmic question here is to find a heating set of minimum size. Right. And this problem is NP complete. Okay. And and a similar problem is the set cover problem. So set cover is it's a subset of the family of ranges, or it's a set of ranges such that every point in the universe is contained in at least one of the one of the ranges in the set cover. Okay. So you can say that this heating set and set cover in the abstract case, they are duals. They are LP duals of each other, and they behave very similarly in many cases. Okay. So that is set cover. Okay. So it's again, like this is used in applications like this. Like you have a number of, okay, so it's sensor networks. So you want you have a client location, and you want to put networks or antenna such that every client location is served. So this can be reduced to a heating set or a set cover problem. Not going into details here. Okay. So set cover and heating set, as I said, it's NP. The minimization problem is NP complete. Even for most of the geometric set systems, it's proved to be NP complete, but you get better results sometimes. Like, for example, the abstract case, there is in case of approximation algorithms, there is a lower bound of log n. Yes, you cannot have an approximation algorithm which gives you better than log n approximation, whereas there are geometric range spaces where you get even a p-task. Okay, you get an approximation algorithm of with an approximation factor 1 plus epsilon, where epsilon can be small. Okay, so and that is okay, that is a motivation for studying geometric range spaces and heating and set cover questions in geometric range spaces, and also it has applications. Okay, so okay, so this is one again. Number of variants of covering and heating problems are studied. I just state some problems that I have studied. One is unique covering problems. So this is a variant of set cover problem. So what is set cover problem? You want a subset, or you want a subset of ranges such that every point is contained in at least one range. Okay. So unique cover is all or some of the elements are covered uniquely. What do I mean by covering uniquely? A point is element is contained in exactly one set. Okay. And these are this variant is motivated by problems where covering a point more than once will lead to noise. Okay. For example, networks case, and a point is in the range of two frequencies, then it will two antennas of the same frequencies, it will form noise, right? So, okay, and there are other variants of the unique covering itself, like depending on whether you want all points to be covered uniquely or some problems to be covered uniquely. There are many variants. So, okay, so I'm just stating some of them. So, all elements must be covered. Okay, so this is the problem. You want every element to be covered uniquely, and you are trying to minimize the number of sets used. So this is called the exact cover problem. And then you need a set cover, but you want to maximize the number of elements which are covered uniquely. The third one is, okay, you just want to maximize the number of elements covered uniquely. Okay. So the first one is a minimization question, and okay, I have written it as a decision variant, but yes. So the first one is a minimization, and these two are maximization problems. So the third one is a unique coverage problem. Okay, so these problems are well studied in the abstract range spaces. Okay, so before there's one more variant, the multi-covering problem. So multi-covering problem is this. So again, set cover is every element is covered by at least one. Instead of saying one, I am saying I need an element to be covered at least C times. C can be a constant or a function, whatever. Right? So these are motivated by multi-covering problems are introduced. These have applications in biological problems. So protein. Okay. So I've studied these two problems, the unique covering and multi-covering problems, for geometric set systems, and studied the parameterized complexity of this. So okay, so this is some of my results. So okay, so for all these three problems, or rather 4 problems, including the multi-covering problems and many variants of it, we have studied the parameterized complexity, and okay, so these are my collaborators at IMSC Chennai, and yes, okay, so we have this result. So these 2 papers, it deals with the parameterized complexity. For these problems, we study like whether there is an FPT algorithm or prove W hardness, and also ask the question whether there is a polynomial kernel, and so on. We also studied the approximation algorithm for these problems. So, okay, so we give a p-task for variants of these problems. Some of these problems, of course, some problems are inapproximable also. Okay, so this paper, okay, so Aniket and they are my I collaborate with them at IIIT-Bangalore. Okay, and so this paper basically gives p-tasks and study the approximability of these problems. Of course, all these problems, see the corresponding heating set version is also studied. Okay, now I go to the next part. This is the art gallery problem. It's okay. So this is one area where I'm working in the last more than 3-4 years. So art gallery is a classic problem in computational geometry. So yeah, it is about this problem, how to guard an art gallery. Started with this problem. So you have an art gallery, and as you know, art gallery usually contains a number of expensive art forms, right? Or paintings, or right. So it is important to guard it. So somewhere in 70s, I think early 70s, in a geometric workshop, they asked this question: how many guards are needed so that every point in an art gallery is guarded? Okay. So that time it was guards. This time you can rephrase this question with cameras, like how many cameras are needed so that the entire IIIT can be monitored. Okay. So okay, so here again, as I said, an art gallery, for that matter, any building can be represented by a geometric figure, right? So this is the okay, I'm not sure about it, I just found it in internet. So this is a 4-floor plan of a part of a Louvre Museum in Paris, it says. Okay. So you get a polygon figure like that. So it's okay, you just need a polygon to work with. So let's, okay, take a more fancy polygon. So given a polygon, what is art gallery problem now? So a guard is inside the art gallery or inside the polygon, right? So it can be represented as a point inside. Okay, and what are the points that can be seen by a guard? Okay, and it's intuitively it's like, okay, if I have a guard here, he can see the entire room, let's say, but he cannot see anything outside. Okay, how do I define it? So if I have another point, these 2 points see each other, or these 2 points see each other if the line segment connecting them lies entirely inside the polygon. So what do I need now to bound the number of guards needed? I need, okay, so the gallery can be represented as a polygon in R square with n vertices, let's say it has n vertices, and a guard location is represented by a point. I need a subset of points such that every other point is seen from at least one point in the subset, right? So this is that gallery problem. Given a polygon, how many points in that polygon need to be selected such that from every other point you can draw a line segment to at least one of those points without going outside the polygon. Okay, so this is the art gallery problem, and okay, I will say this was the first problem to be asked in art gallery area, and this was proved. Again, I think within 1 year or so they gave this proof that a polygon of n vertices can be guarded using n/3 guards. Okay, this proof was first given by Victor Klee, and later an easier proof was given by Fisk. Okay, so this was the combinatorial question. So an algorithmic question is this. So okay, of course, the art gallery theorem says that any polygon can be guarded using n/3. But not every polygon needs n/3, right? So there will be some polygons, like even if you take this room, 1 camera is enough, I think. Right? Okay, so for a given polygon, what is the minimum number of guards needed to guard the entire polygon? And yes, this is the minimum guarding problem, and this is proved to be NP hard. More or less, it is APX hard. I mean, you cannot even expect a p-task for this. Okay, so for all these cases too, of course, you can extend it to 3 dimensions. But okay, I'm not sure, but I haven't seen anything beyond NQ being studied. Maybe more application-oriented things. But theoretically, I haven't seen R square is the this is what I work on. Okay, I'm not sure, but I think then it comes as a factor in most of D will come. The dimension will come as it will appear in the running time. Most of the algorithms are there. But again, it's a general statement. I'm not. Okay, it vary from like which variant and which type of polygon you are. Okay, so this minimum guarding problem is NP hard and it's also APX hard. Um, okay, so after this, so what I said was a general version of a general statement of art gallery, the minimum guarding problem. Of course, a number of variants were studied. Okay, so see, it can be seen that art gallery problems has um, applications, right? Like the statement itself say that it can be used, it has applications in surveillance problems. Also, it has found applications in areas like robotics. Okay, so like again you want to, you want, okay, so you have robots inside a closed space and you want to monitor them using sensors. Okay, it can be formulated as an art gallery problem. Okay. So, and again, a number of variants were studied, and variants can be broadly classified as depending on the type of polygon to be guarded. For example, orthogonal polygons. So orthogonal polygons are polygons where the sides are horizontal or vertical. So these are studied, I guess, because of real world applications. Like most of the real world buildings or other like chips, or they have horizontal or vertical edges, right? So orthogonal polygons and monotone polygons. Then okay, terrains. Okay, I'll come back to terrains shortly. Then the second type of variant is based on position of guards. Where all can you put guards, or where all can you install cameras? Then again there are vertex guards, where guards can be placed only on vertices of the polygon, like corners of the building, or edge guards, where the guards can walk on an edge, along an edge. A point guards basically means that you can put guards anywhere inside the polygon. Okay, and then it is based on type of visibility. What I just mentioned was line visibility. Two guards see each other if there is a line segment between them. That is line visibility. Orthogonal visibility is when the visibility region is a rectangular region. Okay, so I guess it has more implications when you are thinking of cameras and periscope visibility. So these are like some of the variants. Believe me, a large number of variants of art gallery problems are studied. Okay. No, no, no. Yes. So line visibility is basically 360-degree visibility. So you can. This is different from orthogonal. So in orthogonal visibility, you will not see like it's not 360. It's like 90-degree. It's more constrained. So it's more constrained. Yes. And because of that, maybe like you get better algorithms for orthogonal visibility. It has a polynomial time algorithms even for many cases. Better. Okay. Okay. Now I'll come to terrain. Okay. So terrain guarding. So usually when we say terrains, this is what we refer to, like hills, mountains, and some kind of terrain regions. Okay. And it's in like for military applications, it's very important to guard these kind of regions, right? Like in borders and all, right? So you want to guard these type of regions, and so this is 3-dimension, and in 2-dimension, okay, you can think of terrains like this. So they are monotone, and okay, they are X monotone, that is, and you want to guard this part of a terrain. Okay, so just think of some places in the border, and military want to put guards or stations such that to make sure that no enemy is infiltrating. Okay. So it is okay. So in 2 dimensions, you want to guard this the edges of the terrains, and 2 points see each other if the line segment connecting them lies entirely above the terrain. Okay. So so this is the terrain guarding. Of course, 3D also makes 3D is 2D is like a more simplified version of 3D. So the minimum guarding problem, it was proved to be NP hard and APX hard, and it's well studied. Many of these variants, even the general problem, was well studied in the field of approximation algorithms. The first approximation algorithm was given, I think, somewhere around 1987 or 89. Professor Subir Ghosh of TFR Mumbai gave the first approximation algorithm, which is a Logan approximation. Basically, that is reducing it into a set cover. So art gallery can be reduced to a set cover, and then using an approximation algorithm for set cover and give a Logan approximation. And there was no improvement. Nobody could improve this Logan result for a long time. And 2010 there was there was an algorithm which improved it to log opt. Okay, so from log opt to log opt. But it was APX hard. We know that it is APX hard, so you don't expect a p-task for the general problem. But the question whether there exists constant factor approximation, it was open for a long time. Okay, even now it is technically open, but recently, few months back, a group from IIT Kharagpur has announced they have a constant factor approximation, but it is not published yet. The paper is under review, I guess. So if that is true, they have closed a 30-year-old conjecture that there exists constant factor approximation. So this difficulty in approximations is also seen in many variants like orthogonal monotone polygons. But this terrain guarding problem has admitted good approximation algorithms. So constant factor approximations were known for a long time, and again, even a p-task algorithm was it's also the for terrain guarding. Okay, so in approximation algorithm, it was art gallery problem has well studied, well investigated. We look at the parameterized complexity of art gallery problem. So parameterized complexity came, yes. 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 So no. So yes. There is a variant. It's called a watchtower problem, where you can put points here, and yes, so that is inside. But okay, I haven't studied that, but I think it's. It becomes more simpler because of the X monotonicity property. As I said, it has more structure. Yes, of course, point guards, like if you can put guards anywhere, it makes the problem a lot more complex. None of these approximation algorithms work, and yeah, it's not even in NP at all. Okay, right. So parameterized, okay, so it was well studied in approximation algorithms. Parameterized complexity came much later. So I think parameterized complexity is much, it's a younger area with when you compare it with approximation algorithm. The first paper came in 1992. So I think it's still very young, right? It's still in teens. No, teens, not teens, it's past teens, but it's still young, right? So for some time, the big open question in art gallery was whether does it admit FPT algorithms? And quite recently, 2016, this result, Bonnet and Milso proved that it is W hard. Okay, and we looked at the parameterized complexity of terrain guarding. Okay, so of course the general art gallery problem, it is W hard, so we don't expect FPT algorithms. So what about terrain guarding? Is it like, does it admit FPT algorithms? We have this results. So there exists an FPT algorithm. Okay, so minimum terrain guarding is in FPT when the terrains are orthogonal. It's again not general terrain guarding, it's a special case of terrain guarding. We have an FPT algorithm for this, and for a minimum terrain guarding problem, we give a sub-exponential time exact algorithm. That is, okay, so this previous paper by Bonnet, they also show that it's W hat. Also, the general art gallery problem does not admit sub-exponential algorithm. See, if in some cases, like vertex guarding cases, it's easy to see a 2 power n algorithm or an n power k algorithm, right? So this paper, it proved that you cannot improve that to a 2 power small of n. Okay, so but for our result in it shows that for terrain guarding you can have sub-exponential time exact algorithm. So, and these results are important. Okay, so this is because it's the first FPT algorithm known for any NP hard variant of art gallery problem. To the best of my knowledge, as of today, it's the only FPT algorithm known. And this again, this is the first sub-exponential time algorithm for any NP hard variant of art gallery problem. Yes, so we prove n power root k, or can be even seen as 2 power root. Okay, right. So these are our results in terrain guarding. Okay, so this again my collaborators from IMSC Chennai and University of Bergen, Norway. So this paper, it came in ACM transactions. Okay, so this was terrain guarding. And so looked at other variants of art gallery, especially this one, chromatic variant. So chromatic art gallery problem is okay. So this is this was motivated by applications of art gallery in robotics. Okay, so when you have this landmark based robotic control, so every guard, okay, you have a guard set and every guard is given a color, right? And you need the point to be guarded, and also they need to be guarded by a guard of unique color. And this is motivated by frequency allocation, like you have sensors and which monitors let's say robots, and you want a robot to be listening to a unique frequency, so that it's not confused, right? So here the colors on the guards refers to frequency. So this was introduced in a robotics conference, I think. Okay, so it's called a chromatic variant of art gallery problem, and again there is this problem of minimizing the number of colors in this art gallery problem, and this is okay. So I worked on this. Okay, so the earlier work on chromatic art gallery problem was mostly proving bounds, combinatorial results. We studied the algorithmic question of minimizing the colors. We proved that it is para NP hard. That means you cannot even have an n power k algorithm. And of course, therefore, we cannot have an FPT algorithm. And but we give FPT algorithm for some special cases with structural parameters, and okay, right. And also look at this variant of art gallery problems known as the efficient guarding. So this is similar to the unique covering problem. Every point is guarded by exactly one guard. Okay, so this is defined again, it's NP hard, and we prove FPT algorithms exist for special cases. Also give polynomial time algorithms for special polygons. So this work is was with Meghna Reddy, who was an IMTech 2013 student. She recently graduated. Okay, so we have this research on efficient guarding. So Meghna also worked with in the chromatic guarding also, and she has proved, she has given some algorithms there. So that was art gallery. Okay, bichromatic problems. I'll just go a little fast here. So bichromatic problems are problems on point set which are colored using different colors. Okay, so I take the special case where it is colored using two colors, and these are motivated by representation of data as points. So as I mentioned earlier, you can represent data as points in a plane, a higher dimensional plane, and sometimes there are different categories of data, right? Okay, so this can be represented as data with different colors. Okay, so different can be represented points with different colors. Now there are a number of questions that you can ask on this colored point sets. So we start with the simple case of bichromatic point set in 2 dimension. That is points colored, let's say either red or blue, and asking questions on them. Okay, so these, okay, let R and B be red and blue points. So these are some of the questions that we have looked at. The separability problems. You have red and blue points. How to separate red and blue points using geometric surface. Okay, this is motivated, similar to the classification problem in machine learning. And the class cover problem where you think of blue points as, like, say, positive points and red points as negative points, and you want to classify all the positive points together. So it's related to clustering. And then red blue set cover, so universe, okay, you have red and blue points. You want to classify all the blue points and minimize the number of misclassifications, that is, minimize the number of red points that you have covered. So this has applications in fraud and anomaly detection. And so these are like some of the problems that we look at. And so for this red blue set cover, again with Pradeesha, they are my collaborators at Math Science. So we have looked at FPT for different parameters, under different parameterization, whether it admit FPT algorithms or polynomial kernels, also extensively studied in this paper. And then it's separability using orthogonal objects. So this is this I work with my PhD student Abhita and Srinivasan, who was an IM Tech student last year, and we looked at bichromatic separability using orthogonal objects. Okay, so this was bichromatic. Okay, future directions. I'll just mention one direction where I want to investigate the same set of problems or even find new problems. So it is about FPT and approximation. So we have seen FPT algorithms, right? And we know that there are approximation algorithms. Okay? And in both these cases, there are intractable problems. So there are problems which do not admit FPT algorithms. Similarly, there are problems which do not admit good approximation algorithms. Like there are many APX hard problems, for example, right? So for these problems which have their own intractability in the respective fields, can we combine these two to get FPT approximation? That is, can we design approximation algorithm in FPT type? The running time is exponential in a parameter. Of course, you have a parameter. Okay, and of course, let's say you know that problem is W hard, so you don't expect to solve it exactly, but can you solve it approximately? So this is the area of FPT approximation. So now it's pretty it also makes sense in art gallery and number of problems. So FPT approximation is again a recent area, and there is much work on graph problems. So any area, I think the first set of problems to be investigated are graph problems. Any question you start with vertex cover or variance of vertex cover, right? So for FPT approximations are known for a number of graph problems like connected vertex cover and partial vertex cover, disjoint paths and all. right? But it is in the area of geometric algorithms, it is more or less unexplored. So what is the FPT approximation status of geometric problems which are W hard as well as do not admit good approximation algorithms? Okay, so this is one area, and see, okay, so there is here the problem is usually approximations work with optimization problems, and FPT, and at least under standard parameterization, it works with the decision version of the problem. So the first step in defining an FPT approximation is merging this decision and optimization. Okay, it's a long text, I'm sorry for that, but okay, so but this is the definition for, so you come up with an alternate definition for a parameterized minimization problem or a parameterized maximization problem, and you work with this definition basically for an FPT approximation. And taking this a step forward, again you have approximation and you have kernelization, right? So we know that kernelization is useful because it's essentially pre-processing in polynomial time and making the instance size smaller, right? Okay, so but there are problems for which polynomial kernels do not exist, and the problems for which good approximation do not exist. So why can't we merge this? Okay, so instead of, in the previous example of kernelization, the problem and its kernel were equivalent. So you have a solution if and only if you have a solution here, right? So here, instead of looking for exact solution, we are looking, what if we look for approximate solution? Okay, so you have an approximate solution here if and only if you have an approximate solution in the kernel. You need assume like you have some, you are able to prove some property like that. Okay. So again, it's it can be stated like this: you have a C approximation here if and only if you have a C alpha approximation here. Like the same approximation may not be possible, but you are okay to. Okay. Oh, no. This is deterministic, right? Sampling has a lot of randomization into it, right? So this is more deterministic. This is deterministic. Okay. So now this is called again came in lossy kernels. So yeah, this was introduced I think 2014. The first paper on lossy kernels came. They kind of made it into a robust theory of lossy kernelization. Basically means kernelization with some loss, like you loss, as in it's not exact solution, you lose something from the exact solution. So lossy kernel. So for problems which do not admit polynomial kernels, can we at least have polynomial lossy kernels? Okay, actually it makes sense in a large set of questions, and as I said in the term for geometric algorithms, it is more or less unexplored. I haven't seen any result in geometric algorithms. So all of these problems like this covering, set covering, hitting set problems. So geometric, many of these problems they give a p-task, but okay, I see all of the geometric problems that I've seen. They give a p-task, but they will not give you an EP-task. So it will not give an efficient p-task. Can we get, so in this context you can ask, can we get EP-task, or can we get what they call as an EP-SAX, that is efficient approximation kernelization. Okay, so can we have an EP-SAC, or similarly we have fully polynomial like FP-SAX also, analogous to the FP-task in an approximation. Okay, so all these questions are open, and it will be interesting to look at these for all these set of problems and even identify new problems. So yes, so that is that's where I hope I can contribute more. So yes, so that's it. So thanks for listening.